Now we're going to use the techniques that we've had and the equations that we've had, and we're going to try and solve simple trig equation, just find out where cosine of z equals j. So we're trying to find values for z that make this a true statement. Okay, so we need to have our addition for cosine we're going to start with, which from the previous session is a half e to the jz plus e to the minus jz. That's just our definition for complex cosines, and that equals j. And the way we're going to solve this thing is we're going to basically make a quadratic out of it. So I'm going to multiply that 2 up and bring it over to this side. So I'm going to have e to the jz minus 2j plus e to the minus jz equals 0. And I'm going to use the same trick I used when we were doing the catenaries. I'm just going to multiply everything through by e to the jz. So I have e to the jz squared minus 2j e to the jz plus 1 equals 0. Okay, because for this one, e to the minus jz times e to the jz, you add the powers, gives you 0, and e to the power of 0 is just equal to 1. Okay, and this is a quadratic in e to the jz, so it's like x squared minus 2jx plus 1. So effectively it's a quadratic with a, the first term being 1, b being negative 2j, and c being 1. So I'm going to use the quadratic formula, which tells me that x equals negative b plus or minus the square root of b squared minus 4 lots of a times c, which are both 1. So I just end up with that, all divided by 2 lots of a, which is 2. Which gives me, what have I got, 2j plus or minus the square root of, okay, 2j is going to be 4j squared, which is negative 1, so it's negative 4 minus 4 is negative 8 over 2, which is, can cancel out some 2's here, so we're going to do with j plus or minus, okay, negative square root, so j, and root 8 is the same as 2 root 2, so I'm cancelling out the 2, I'm just left with root 2, so it's j, and then in brackets 1 plus or minus root 2. Okay, so that's my expressions for e to the power of jz is equal to this thing, which is going to give us 2 possible solutions, once with the positive root and once with the negative root. So I'll do the positive root, and I'll leave the negative root for you to have a crack at. So the positive root, I just mean that e to the jz is j1 plus root 2, and I'm trying to find z. I'm trying to rearrange this thing to give me z. So if I want to get z out of this, I have to do the natural log of this side to undo the e, which means I have to do the natural log of this side. So it's the natural log of a complex number, which means I want it in polar form. So I need this number in polar form. So if I'm looking at this number in polar form, this is the real axis and the imaginary axis. This number is all imaginary. There's no real bit, it's just imaginary. So it's just up here at a height of 1 plus root 2, and the angle is 90 degrees, which is pi over 2. So what I'm saying is that e to the jz is 1 plus root 2 e to the j pi over 2. Okay, so what I've done is I've taken this effectively rectangular form, well that's pure imaginary, and I've made it into exponential form, and now I can do the natural log of both sides. So if I log both sides, I get jz is the natural log of 1 plus root 2 e to the j pi upon 2, and what we've seen previously is that gives us the natural log of 1 plus root 2 plus j pi upon 2 with the old 2 pi k floating around there. Okay, so that's jz. So to get z by itself, I just need to divide through by j. So z equals this thing, and dividing through by j is the same as multiplying by negative j, because if I multiplied this side by negative j, I'd have negative j squared, which is negative 1, which is 1. So I'm going to multiply through here by negative j. So this will become the real bit. So negative j times j is negative j squared, which is negative 1 is 1. So this becomes the real part. So I get pi upon 2 plus 2 pi k is my real bit. I'm going to multiply this thing by negative j, so it gives me minus j log 1 plus root 2. Okay, so I've managed to solve the cosine of z equals j and gone through a bit of a process, and I've come up with, unsurprisingly, an infinite number of solutions because it's cosine is a cyclical function, so you're going to have repeating terms. And these are purely good, solid, rectangular, complex numbers. There's a real bit, and there's the imaginary bit. And then you want to repeat the whole process, which I'm not going to go through all the process, but I'll give you the answer so you can check it. For the negative root, so the negative root's just starting from here with that minus. So we go e to the jz equals j1 minus root 2, and then we follow through the same process, and we should come up with z equals 3 pi upon 2 plus 2 pi k minus j natural log root 2 minus 1. Okay, and that's the negative root of the equation. So reasonably involved. Again, something unlikely you have to do at an exam level, I would imagine. But again, something that's well worth having seen. And it's got those useful things into the game. This whole idea of turning something with a positive and a negative exponent into a quadratic. That standard trick that we've used a couple of times before. And the key idea that if you want to be able to do the natural log of a complex number, you have to have it in exponential form before you start.